Next up, I want to talk about sampling, and I want to talk about sampling with and without replacement. When you think of sampling, you might think of a number of things. For example, you might think of Sean Puffy Combs, who's has sampled lots of music in his days as a hip hop producer. That's not the kind of sampling that I want to talk about, but it is good sampling nonetheless. Sampling that I want to talk about is if you have a large group of objects. If we select one of the objects at random and we can inspect it, we can sample it. That is what sampling is. If we just take something and then look at it from a pool of other objects. And you've actually heard of this before. Might not have called it sampling though. If the object is put back into the group, into the object, it's called sampling with replacement. You have replaced the thing that you have removed, put it back into the pool from which you've taken the thing. If you don't put it back, if you were to take an object to inspect and you were to remove it completely, that is called sampling without replacement. Kind of makes sense. And so one place that you see this happen is when you look at population information or when you hear about polling information, things like that. You'll notice sometimes you've heard a survey result comes out and you think, hey, they never asked me about this. And that's because what happened was there was a sampling that was done where some of the people in this pool were sampled and maybe you weren't. But that's what we mean when we say sampling. Selecting some from a pool and either inserting them back into the pool for more sampling or removing them for more sampling. Some key concepts with sampling is that sampling is usually used in the areas of quality control of the industrial process. And sometimes the inspection process is made and it's impossible to return something back to a large group. And so you might see sampling occur without replacement if you were to work at a chocolate factory to see if it is hard or soft-centered, and you need to bite it or squeeze it. You're not going to put that back onto the assembly line to go out to be shipped somewhere. So you might sample something and then you'll have to discard it. That would be sampling without replacement. Or if you wanted to see if an egg contains one yolk or two, if you wanted to sample a series of eggs to see what's going on with them, you have to break the egg. You can't put the egg back together. So that would be sampling without replacement. Or if you want to see if an object is correctly made, you sometimes need to pull it apart and inspect it. These are sampling items that happen in the industrial process where you are mass producing items and you need to see kind of like a quality control, see how they're working. What we're going to talk about is marbles, because that's what we like to do in probability. And here I've got two tree diagrams for you, and this would be after pulling two marbles out of this bag. If I were to use replacement, if I were to sample these marbles, if I were to take one out, inspect it, and replace it back, that's what this left-hand tree diagram represents. So here's my marbles. I've got 2 blue, 1 yellow, 3 red. And the first marble that I remove can follow this tree diagram, where there's a 3/6 chance that I pull a red, a 2/6 chance I pull a blue, a 1/6 that I pull a yellow. And if I replace that back in, then there's the same probabilities exist for that second marble, 3/6, 2/6, 1/6. If I were to not replace that first marble, if I were to pull out a marble and then throw it away completely, chuck it somewhere else, then the probabilities do change for that second marble. So same first probabilities as before, but now you'll notice that the size, the sample size, has decreased by 1 since I have removed one marble. So if I take a marble out, then that's going to change all of my next probabilities of that second marble. So notice what happens here. When I take out a red marble first, then I have one fewer red marble. So if I were to remove a red marble from this branch with that first marble, now you can look at all the probabilities. I've got 2 out of the remaining 5 that could be red, 2 out of the remaining 5 could be blue, and just 1 out of the remaining 5 could be yellow. What if I were to remove a blue? Then I get rid of a blue, and now there's 3 out of the remaining 5 that are red, 1 out of the remaining 5 that are blue, and 1 out of the remaining 5 that are yellow. So the big takeaway here is when we say without replacement, that kind of changes the landscape of our sample size, or sample space rather. And so that the branches need to reflect that. And that's just something to keep in mind as you're drawing these tree diagrams. Are we replacing the things, or are we without replacement? So if I were to take these independent events and say that they are with replacement, then the pulling of these marbles don't impact each other. With replacement kind of implies independence with the events. We could say the probability of drawing 2 reds, we're going to multiply red times red, 1/2 times 1/2 to get 1/4. But if I were to look at the without replacement, this is kind of like a dependent event, right? Because the tails of all of these depend on what happened before them. You'll notice here, actually, I didn't say this before, but you'll notice there's no two yellows in this first yellow branch, and that's because there's only one to begin with. So the probability really changes. If you draw yellow first, then you only have two possible outcomes after that branch. So when you do not replace items, now we're talking about dependence with these probabilities. So without replacement is I'm going to multiply the probability of grabbing two reds, which is again red and red, but now this is 3/6 times 2/5, which will give me a chance of 1/5. So I have a greater chance of pulling two reds if I replace my marbles. So let's see an example of what this looks like. If I have a box that contains 3 red, 2 blue, and 1 yellow marble, I want to find the probability of getting 2 different colors. So if that sounds familiar, that is because it's the exact same tree diagram we were just talking about. We want to talk about what the probability is of getting 2 different colors if replacement occurs, and then if replacement does not occur. So let's take a look at that tree diagram we had from before. You can ignore this blue then R, or blue then red, because that's not relevant to what we're doing right now. But if I wanted to find the probability of getting 2 different colors, I have to think about what all of those branches are. So that could be a red and a blue, a red and a yellow, a blue and a red, a blue and a yellow and a red, or a yellow and a blue. All of these items contain probabilities that result in 2 different colors. And this is with replacement. So all of these probabilities are the same with each of the iterations of these, or each of the events of these branches, since they're independent of each other. So to get what the total probability is of all of these things, I need to take the total probability of each of these branches, each of these outcomes. So it's 3/6 times 2/6, which is going to equal 6/36. And then let me take the outcome here. This is 3/36. This check mark here is the path that gets me from blue to red, and that's going to be 6/36 also. This next path from blue to yellow is going to give me 2/36. And from this path here was 1/6 and 3/6, so that's going to be 3/36. And then 1/6 to 2/6 is going to give me 2/36. One thing you might notice that actually I didn't mention before is a lot of these fractions can be reduced in my tree diagram, but it's kind of helpful that I didn't reduce them. It's a good thing that I didn't write this as 1/2, because now when I want to add all of these up together to find that total probability of 2 different colors, I have a common denominator. So this is really easy to add up together. So the probability of getting 2 different colors is going to equal the probability of pulling a red then blue, plus the probability of pulling a red then yellow, plus the probability of grabbing a blue then red, plus the probability of a blue then yellow, plus the probability of a yellow then red, plus the probability of a yellow then blue. And that's the different outcomes that I have reflected here. When I add all these things up, I get 6 plus 3, that's 9, 15, 17, 20, 22. So that is 22 out of 36, which is equal to 11/18. And we'll leave it just like that. That is the probability of grabbing 2 different colored marbles when I'm talking about sampling with replacement. So let's talk about letter B, if replacement does not occur. So that's this other branch that we talked about before. So if I were to pull out all of the paths that I'm interested in here, I've indicated these with these X's. It's the same paths, but you'll notice that the probabilities have changed. So why don't we do the same things we did before? The probability that I will end up at this branch is going to be given by 3/6 times 2/5. So that's going to be 6/30. The probability that I draw a red then a yellow is 3/6 times 1/5. So that is 3/30. I really feel like I'm working on my fuzz in this section of the video. The 2/6 times 3/5 is equal to 6/30. And then over here, 2/6 times 1/5 is 2/30. And then over here, 1/6 times 3/5 is going to give me 3/30. And then finally 1/6 times 2/5 whew, is 2/30. I think I need a drink of water after all that. Feeling better. Okay, and just like before, to find the probability of two different colors is going to be the sum of all those probabilities that we listed just already before. But now the only difference here is that we don't have that replacement, so we've just changed the probabilities of that second event. So when I add all this stuff up, I get 6, I get 9, 15, 17, 20, 22, and this is going to equal 22 again, but this time it is out of 30. So this will reduce down to 11/15. So it's actually a greater chance that I will have two different marbles if I do not use replacement. How about that? So a lot of thinking goes into these types of problems, and it really is helpful to draw a picture or to really spend the time carefully constructing these tree diagrams. So I want you to try that in this you try example, where we have marbles being drawn, and again I want you to diagram what happens if we use replacement and what happens if we don't use replacement. So determine again the probability of drawing two different colors. So pause the video, spend the time drawing these diagrams correctly, and see if you can't get the answer. All right, and here's my final solution for this one. I've drawn out my tree diagrams. This would be with replacement, this would be without replacement, and the final answer for letter A with replacement is 20 out of 49, and without replacement, the probability of getting two different colors is 10 out of 21. So hopefully this is going okay for you.